Okay, so then I'm just going to start the lecture, and we can talk about the exam on Tuesday. All right. So I'm going to skip this for now, and we'll go directly to the lecture. How many of you guys weren't here on the Thursday? On Tuesday, I mean. You, Mr. Wang, who else? Anyone else? Mr. Su, anyone watching videos? Please lower down the volume. We discussed a few very important things on Tuesday. Is that noise coming from outside? Yeah? Okay, I'm going to close the door. Just wait a second. We discussed a few more things, including the anisotropy of rocks. I don't know what's going on with this. That we cannot see the full screen. Hey, Simon, could you take a call somewhere else? Thank you. Okay, yeah, I don't know why this is smaller, but let me try to fix it very quickly. What do you think, guys? Which one it is? Probably that one? Let's try. Yeah. Okay. Okay. Source. How do I get out of here now? No. Okay, so we discussed about the anisotropy of rocks. Rocks are never homogeneous. They are not isotropic. They vary as you move along and as a function of space, and they are also very anisotropic. Most sedimentary rocks, they have layers, fine layers or thick layers that make the rock very anisotropic. And that anisotropy makes a rock to have elastic moduli or Young modulus and also Poisson ratio, which are different in different directions depending if you take a rock sample horizontal with respect to bedding, vertical with respect to bedding, or at an angle with respect to bedding. And it's not only the elasticity what is different, but also rocks tend to have a very strong strength anisotropy. So the maximum stress that they can take also depends on orientation. And many times that's due to the lamination of rocks and the presence of weak interfaces. Whenever you have interfaces between the rock that are weaker than the two separate rocks, in this case, those two themselves, then you can have a very strong strength anisotropy. If you were to fail these different type of rocks, horizontal with respect to bedding, vertical with respect to bedding, or at an angle with respect to bedding, you will get to see different modes of failure and different types of fracture that you can encounter in this type of rock. And unfortunately, we do not have enough time to go in detail about this issue, but I hope that you remember that this is very important for wellbore stability, especially when you drill in formations with deviated wellbores. As you drill and you deviate your wellbore, the stresses that you apply on the wall of the wellbore are going to load the rock in different directions. And the strength of the rock or the stability of your wellbore is going to be a function of the angle of the wellbore. We're going to see that later on in wellbore stability. But remember that the rocks are not isotropic. What we're doing is just a simplification with our elasticity theory. Okay, so, and then we talked about another very important topic, which is compression failure. We talked before about tensile strength, how rocks can fail in tension. We talked about shear failure. And there is one more type of failure, which is compression yield or compression failure. This is the point at which you compress the rock so much that you may not have fractures very well defined, but your rock just fails internally. Some of the grains, they break, and the rock deforms quite a bit more than what it would in these other types with shear or with tension. Instead of having, in these cases, a shear fracture or in tension, a tensile fracture, in this case, you will have failure all over the rock without being concentrated in just one small region. And in these cases, sometimes also you can have some small, when there is quite a bit of shear, some small fractures inside. But they also tend to be quite spread out, and they are not localized as in those cases. Why compression failure is important? Because many times we subject rocks to increased effective stress, and this is mostly due to depletion. When you lower the pore pressure in a reservoir, you increase the effective stresses, and the magnitude of the increase of effective stresses depend on the magnitude of the decrease of pore pressure. Can you tell me about any other example where you may crush, let's not say rocks, but you may crush sand? Can you think about anything like that? I had an exam some time ago related to a question like this. Can you imagine about any application where you crush sand, or you may crush sand? Ideally, you shouldn't. I'll give you a little help. Any hint of what I might be drawing? This is a fracture, very well. Probably the width is kind of exaggerated. I should make my wellbore a little bit bigger. If you have a fracture and you prop it with sand or with some synthetic propants, when you deplete the formation, also you lower the pore pressure, similar to what happens in this case. As you lower the pore pressure, you increase the horizontal stresses as well as the vertical stresses. But let's imagine this is a vertical fracture. After a long time, you may have your propant that was originally spherical to break and to crash with small pieces that are generated around the propant, which it might not be good because it lowers the permeability of the propant. So this compression failure, it's also very important in many applications, mostly related to reservoir depletion. This is a very important and kind of conceptual concept here that you know, for example, if you were an aerospace engineer and you were designing a plane, you design the wings in order to resist stress because you're adding a load on the wing. Say because it's loaded, it's resisting the pressure in the wings, and that is making the wing deform, right? Or if you were a civil engineer, you will design the foundations or the rock underneath the building to resist a weight that you put on top. But these are always sort of external forces that you apply, and you design whatever resists that in order to support those forces. In our case, notice that we don't add anything. We extract fluids, in this case, in order to recover valuable hydrocarbons, and we increase the stresses by extracting something inside the rock. So in this case, we don't add anything. We extract fluids, and that's the way that the rocks get loaded and effective stresses increase. Okay, and then as a summary, we talked about all the types of failure. If you start with an original in situ stress, you can modify that in situ stress by adding a well bore, by adding a hydraulic fracture, by lowering the pore pressure, by injecting a fluid, by injecting a cold fluid, by doing all type of operations. You can change the state of stress, and it can go sometimes into tension, for example, at the tip of a hydraulic fracture, into shear, as for example, you inject fluids and you cause full reactivation, something we're going to see in a little bit, or you can go into compression, for example, when you decrease the pore pressure and you increase the stresses from all sides. So all of them are very important, and all of them bound all the possible state of stresses in the formation. You cannot change the formation stress too much. Many times it's going to reach one of these boundaries, and it's going to fail. The rock is going to fail with some sort of type of these failures. And notice that this is very important, because when you fail a rock, when you create fractures in rock, what do you think is going to happen to the permeability? It may increase if you have, say, a tension fracture, or if you create hydraulic fracture. Right now your rock, if it was not fractured, now it has fractures inside. If you have shear fractures, it depends. It's a little bit more difficult to say what's going to happen. Sometimes it increases, sometimes it decreases. When you have compression failure, most times it definitely decreases. So with geomechanics, and this is now what is important about geomechanics, is that permeability is not a constant parameter. It's something that you can modify. And that's why geomechanics now is very important, because, for example, with unconventionals, we do not stick to the original permeability of the reservoir. That's something that you can modify. And in order to modify in the way that you want, you have to be smart in order to create the types of failures that are going to increase permeability and are going to favor fluid flow in the directions that you want. That's our objective in geomechanics. It has two sides. One is to modify initial permeability of reservoirs, or to guarantee the permeability remains high, and the other side is to avoid some unwanted implications of changing fluid pore pressure in reservoirs. Like, for example, we don't want induced seismicity. We don't want subsidence. We don't want case shearing in the subsurface. The work of the people that works in geomechanics try to balance those two, the benefits of geomechanics, and also try to avoid the unwanted implications. Okay, so we're getting very close to going to applications of geomechanics. There is one more thing that I'd like to talk about failure of rocks, and then we'll get into fault stability. And this is something which is called brittle to ductile transition. What is a brittle failure? Probably you all know about this. So let's say I have a solid that I'm failing under a triaxial stress condition where this is sigma 1 and this one is sigma 3 and this one is sigma d equal to sigma 1 minus sigma 3. What do you understand for brittle? And anyone can give me an example about that? A brittle failure? Well, let's, if you have fractures, that adds one more level of complexity. Let's imagine that we don't have fractures. We start with something with no fractures. A brittle failure is a failure in which when you break a material, it breaks very quickly and it breaks in very well-defined planes. Like for example, when your cell phone screen cracks, have you seen how it cracks very quickly? Well, sometimes it may crack slowly too. That's another type of failure. But if you were to drop it and fail it very quickly, it will shatter, right? And then all the screen will be plenty of fractures with very well-defined fractures. If we were to run a test on a brittle rock, you will see that you can load it, and probably this is what happened to you with the Boise sandstone and the Berea sandstone, that you load it, and up to a point, it reaches a peak, and then the stress goes down very quickly. Why it goes down very quickly? Because you form fractures very quickly too, and those fractures cannot resist stress anymore. And because of that reason, this stress goes down very quickly. And in this case, I'm running tests with constant strain rate, which what means is that what I'm controlling is I'm moving the plate at a constant velocity. That's exactly what you do in the laboratory as well. Well, it turns out that rocks can be brittle, but also can be ductile. And it actually depends on how much confining stress you have. So the same rock, if you were to add more confining stress, you will see that it will be stiffer, it will be stronger, and it will eventually become more ductile. A brittle failure, then, as we said before, is a failure that happens very quickly. You form fractures in very well-defined planes. A ductile failure is a failure in which you do not have a well-defined peak, and the deformation may not be very well localized in a single plane. So if we have, this will be increasing sigma 3. If you have a brittle failure, your rock will fail in very well-defined planes. If you have a ductile failure, your rock is going to deform a lot volumetrically, and it may have failure in several locations and maybe not very well localized. I have an image about this that I'd like to share with you in the notes that is going to help make a point here. I'd like to remind you too that next week you have the triaxial test laboratory. In that triaxial test laboratory, you're going to do this type of triaxial tests. So let me find the. So, okay. So this is what we have been explaining, and here you have a nice example of brittle failure on the right. So you see very well-defined fractures, and ductile failure, in which the rock fails almost everywhere, and there is not very well-defined fracture. Which one do you think is going to increase permeability? The brittle failure or the ductile failure? Why?
Because it looks like the fractures have opened up more and they're better connected.
In summary, yes. Yes, the brittle failure will be better for creating fractures that are connected. And if you have also a low confining stress, you may have something which is called shear dilation, which means that the fractures, in order to go on top of each other, very similar to grains going on top of each other, because the fractures have asperities, the fracture is going to have to dilate in order to go on top of the other face. So that's going to make the permeability even larger. In the case of ductile failure, the pore space is going to increase everywhere, and you may not have dilation. It's going to be mostly a contraction. So the porosity is going to increase everywhere, and you may not have failures that are well connected for permeability. Yes, Ms. Montero.
Are we assuming that sigma 3 is the confining pressure?
Yes. In here, let me come back over here. Here, sigma 3 is the minimum effective principal stress, and sigma 1 is the maximum effective principal stress. When you take it to the laboratory, sigma 3 is going to be the confining pressure minus the pore pressure. But in general, this is a function of effective stress. So the more effective stress you have in the rock, the more ductile is going to behave. And remember that we're talking about the same rock. Some of you, it depends on which group, and it depends what Jeffrey gives you, but you may work with this Texas cream limestone. That's a very soft rock, and at the magnitude of confining pressures that we're working in the lab, up to 1,000 psi more or less, you will see this transition from brittle to ductile. When you broke, can you raise your hand if you worked before with it? You all did, right? So you all did the Texas cream. So if you notice, that one was weaker, was softer, and also, but when you fail it in unconfined compression or in tensile strength, it formed very well defined planes. Well, now there is going to be a group in each day that is going to work just with Texas cream, another group just with Boise sandstone, and another group with Berea sandstone. For the Texas cream, at the confining pressures that you're going to work in the lab, you're going to see this transition from brittle to ductile. You'll see that the rock at 1,000 psi of effective mean stress is going to deform a lot more like this and not like that. And you may not be able to recognize very well-defined fracture planes. With the Berea sandstone and the Boise sandstone, it's going to be a little different. Those need a higher magnitude of mean stress in order to develop this brittle to ductile transition. But they do that as well. It's just that you need higher stress. So this behavior is going to be very important because as we were talking about a modification in permeability, the effect and the implications of that type of failure is going to be quite different. Many times when you go into unconventionals, what you want to do when you drill a wellbore, and after you drill a wellbore, you do hydraulic fracturing. We're done with drilling. We're going to do the fracturing. Many people look for a parameter of the rock that some people call rock brittleness. And this is going to depend on many things. But one of the parameters that characterizes rock brittleness that more or less works well is that the brittleness is going to be proportional to the Young modulus divided the Poisson ratio. The lower the Poisson ratio, the higher the brittleness of the rock is going to be, and the stiffer the rock, also the bigger the brittleness is going to be. If you were to have, let's say that rock, we're going to divide it in two types. One which is ductile, and another one which is brittle. If you were to do hydraulic fractures in ductile formations, you will tend to form mostly very well-defined fracture planes and more or less fat fractures with a little bit, or quite a bit of ductile failure around the fracture, but not very well connected. Very similar to what we saw in the images before. So why are these fat fractures? Because the rock, if it's ductile, will tend to have more plastic deformation and will allow those fractures to have a bigger width. We're going to have failure around the rock, but it's not going to be very well connected. And if you were here on top measuring microseismicity, do you think you will measure microseismicity? When you run the laboratory in the test of unconfined compression, did you get a very loud like bang sound with Boise Sanson? Some of you did, right? So all of that is elastic energy which is being released very quickly and in form of waves. In this case, you hear a bang because all that rapid dynamic energy is getting into a pressure front that you hear as a bang, right? But if you had a rock failure in the subsurface, you wouldn't hear anything, but you may measure some seismic activity. But in the case of the ductile failure, do you think you will hear a lot of microseismicity or not? No, right? I hope you kind of picture this, why this is the reason. But in ductile failure, you spend a lot of energy. Remember that the integral underneath this is energy. You spend a lot of energy deforming the rock. And most of the energy goes into this sort of viscous deformation. In brittle failure, you spend the energy in creating fractures. And the fractures, they slide very quickly. And that slip of the fractures very quickly release all the strain energy of the rock. So in this case, probably this microseismicity is not going to travel very far. And your fractures, you're going to be able to place fractures, but probably the communication is not going to be great. What about if you make now hydraulic fractures in a brittle and stiff rock? Here, you will tend to have thinner hydraulic fractures, which are also, as you place those hydraulic fractures, are going to reactivate the rock and create planes of failure that may fail in shear. This is something we're going to see later on, that are going to break the rock and create more paths for producing fluids more quickly. And because now this failure is brittle, very likely you're going to measure quite a bit of microseismicity that is going to be measured on surface, and is going to indicate that you actually have brittle failure in the rock and not ductile failure. And we're going to get this in a little bit after we discuss brittleness. If you were to take the produced water and inject it into a deeper well in which there is a fracture, there is a fault. So now we're getting into this is a very permeable formation, and let's say that this is close to the basement. So this is, I'm here with these schematics, I'm trying to draw igneous rock. It matters a lot what is the type of rock with fault reactivation. If you have a ductile rock, like for example a soft limestone or a soft mud rock or an unconsolidated sand, if you have fault reactivation and this one slides, probably if this is ductile, you will not have earthquakes. You will not have induced seismicity. However, if you bump into increasing pore pressure into a fault that has very brittle rocks, like for example igneous rocks are very brittle, right? If you grab a hammer and you